Hi, in this lecture we will be talking about the electronic nature of atoms, and we start with a quote from Erwin Schrödinger, who said that what we observe as material bodies are nothing but shapes and variations in the structure of space. And in the later part of this lecture, we hope that we can also reflect on this quote and whether we believe it or not, or examine the merits of this quote also. What led him to say such thing? So our learning targets for this lecture are to explain the electronic structure of atoms in terms of main energy levels, sublevels, and orbitals. We will focus on the energies or energetics of electrons. Our second goal or learning target is for us to relate quantum numbers to the placement of elements in the periodic table. Okay? So I'll give a brief review on a few concepts, a sort of tracing back of the history of the development of the atomic model. But I do hope that you have already done this in the previous virtual lab, which was our Springboard 0.3. Okay, so we remember that electrons can behave as particles and as waves. So first, let us think about electrons as waves. Electrons behaving as waves fall under electromagnetic waves, so there are two components which are perpendicular to each other. And when you say electromagnetic wave, a wave is a disturbance in space that carries energy. And when it is electromagnetic, it doesn't require a medium to transfer that energy, or the wave does not require a medium to travel. And then we also think about the electromagnetic spectrum. Okay, this is the arrangement of EM waves or electromagnetic waves according to their wavelength. Okay, so the higher wavelengths are found in this side, while the shorter ones are in here. The gamma waves are very compact in this side. But we will concern ourselves with what is visible. Okay, visible light, and then in this region that's in between infrared and ultraviolet. Now, I do hope that you have already encountered these terms as you've used it in the virtual lab. So we will concern ourselves mostly on UV and visible light. So the UV-vis spectrum. Now we can also think about electrons as having particle-like properties. When you say particles, what distinguishes a particle from a wave is that a particle has mass, okay? And then waves have certain characteristics, have certain phenomena that can also distinguish them from particles. But for now, we will talk about the photoelectric effect. So in the photoelectric effect, okay, you have here a certain setup, and then this is a vacuum, and then you have an open circuit initially. Okay, but what happens here is, if this is your positive terminal, this is your metal rod, and this is a metal surface. Okay, it's a highly metallic one, so electrons can travel and can be delocalized. If at first there was no current that was registered, but they found out later on that when you radiate this metal surface, some electrons have been knocked off and they transfer to the positive terminal. Okay, so again, at first there was no current that was registered. Okay, the setup is doing nothing at all. But once radiation was experienced by this metal surface, they discovered that there was already a signal. Okay, there was a recording on the current. So what could have happened? So they postulated that electrons travel from the metal surface to the positive terminal. Okay, unlike charges get attracted to each other, so electrons which are negatively charged get attracted to the positive terminal, and then electrons also flow such that there was a registered current. Okay, of what happened in the photoelectric effect. Okay, so light was irradiated on a metal surface, and they found out that there was a registered current. So the meter indicates an electron flow. So what could have happened? There were some electrons that were knocked off from this surface to the collecting panel, to the positively charged part of the circuit. Okay, so electrons are attracted to and collected here. Okay, and this was initially a vacuum. So what could have happened? Okay, so that means electrons have exhibited particle-like properties. They actually have mass, right? So another important concept is on emission spectra. Okay, when you say emission spectra, these are bright lines or bands produced on a photographic film by radiation, okay, or for example by light, okay, any type of radiation that has passed through a refracting glass prism after being emitted from from thermally excited atoms. So when you say refracting glass prism, a simplified construct for this is that when something refracts, it bends. So what is being bent there is actually your radiation. So think of white light being refracted into the colors of the rainbow. Okay, but there is a significant difference here. When white light, when visible light is refracted, okay, by a prism, you get a continuous spectrum. Okay. However, if you have a hot gas, okay, or vaporized atoms, for example, sodium or lithium, you vaporize them, you heat them such that they exist as free atoms, okay, and then what happens was that a radiation results from them. Okay, there is an emission of radiation. That's why it's called emission spectrum. However, once it is refracted, once it is bent, we do not get a continuous spectrum, but we get discrete lines or discrete bands. So this is an example of an emission spectrum. Okay, the singular form of spectra is spectrum. Okay, and then there's another type also called using cold gas, but we won't concern ourselves with this very much. So if you remember in your experiment, we'll go to this first. So imagine this is a light source and this is white light or visible light. It separates into a continuous spectrum. But if you remember in your experiment, we were talking about the models of hydrogen atoms, no? And then we found out that there were some lines which have been formed on the spectrometer. So for atoms and molecules, one does not observe a continuous spectrum. Okay? They found out that each element has its own corresponding atomic emission spectra. So they use this to distinguish all the other elements from each other. Why? Hydrogen has its own atomic emission spectra. Helium has its own spectrum. Uh, what is this? Xenon has its own spectrum. Okay, all unique, all different from each other. So we relate this into the line spectra of hydrogen in our virtual lab. Okay, this is the actual atomic spectrum for hydrogen. Okay, composed of this one, the blue, green, and the red light. Okay, each with its corresponding wavelength. So in the experiment in the virtual lab, okay, if you have more enough time, when most probably you will also end up with something like that. Okay, because we are studying with the same element, that's hydrogen, and hydrogen has its unique atomic emission spectrum. All right, so there is this development now. What could we use to explain the uniqueness of those atomic spectra? Okay, what resulted into those different atomic spectra for each element? Okay, so if we try to look at the line spectra of hydrogen, so remember that in Bohr's atomic model, he actually described it, he used it to explain those results in the emission spectra. Okay, so he just said na maybe there are fixed areas around the nucleus wherein the electrons have specified energies. Okay, and then they travel there without releasing their energy, without releasing light. However, if we heat them, the electron goes up an energy level or goes up another energy level, and then it goes back down to its original energy level, and then that's what results into the different colored lights, the different photons of different wavelengths. So for example, if this is your hydrogen atom, and then at this part is your nucleus, the positively charged nucleus. So if one electron jumps from N1 to N2, or in here from N3, it goes down, so it emits red light from N3 to N2. Okay, and then for example, if the electron has reached as far as N4 here, but then it goes back to N2, N2 lower. Okay, remember that these are excited electrons. You heat them up. Okay, you heat the atoms up, so the electrons get excited, so they jump from one energy level to another. So from N4, if it reaches down to N2, it emits blue-green light. Okay, so that's why we have these different colors in the atomic emission spectrum for hydrogen. Okay, so I'll pause for a few moments and let's see if you have questions. Please pause this video and then note down your questions so that we can discuss it in the synchronous session. So in order to explain those results in the atomic emission spectrum for hydrogen, the idea of the planetary model was developed. Okay, so Bohr suggested that each electron is residing in fixed orbits, just like planets around the sun, okay, where there is no change maybe in energy, but if you excite them, they can move from one energy to another. Okay, so that's the idea of having quantized energy comes in. So when you say quantized, fixed amounts of energy in discrete orbits. So meaning to say, in order for an electron to move from one energy level to another, from one orbit to another, then there is a specified amount of energy needed. All right, and there is a fixed amount of energy needed. And so you have this kind of graph. So it shows here a little bit of math, but we'll deal with them later on. Okay. So these lines here represent the principal quantum numbers. So from the n is equal to 1, okay, so the orbit nearest to the nucleus, it takes quite a lot of energy to reach n is equal to 2, okay, and not as much energy to reach n is equal to 3, and then lesser difference already for n is equal to 4 and n is equal to 5, so on, right? So here are the implications. Number 1, electrons in an atom can only occupy certain orbits corresponding to certain energies. Now they have extended this idea not only to hydrogen but also to multi-electron atoms, the larger atoms, lithium, iron, the heavier ones also. Okay, so first, electrons can only occupy certain orbits associated with their energies. Second, electrons in permitted orbits have specific allowed energies. Okay, specific allowed energies. These energies will not be radiated from the atom considering the same conditions. So if you do not heat it at all, then the electron continues to revolve around the nucleus in that particular orbit, in that allowed energy level. All right? And the third one is energy is only absorbed or emitted in such a way as to move an electron from one allowed energy state to another. Okay? So again, energy here is quantized. You can only move an electron for a specific amount. So there is a specified required amount of energy to move it from one energy state, energy level to another. Okay? And then there were also some experiments later on, some mathematical proofs that have been developed, but we'll not discuss them any much further. We'll just give the main idea. So Louis de Broglie also posited that if light can have material properties, then matter should exhibit wave properties. Now, in your physics later on, you will talk about these wave-like properties, such as diffraction. You'll talk about the double slit experiment, but we reserve that discussion for later. So, Louis de Broglie also demonstrated that the relationship between mass and wavelength was given in this equation. Okay, again, h is Planck's constant, but we will not be dealing too much with the math here, so good for you. But what the main idea here is they are reconciling, okay, they are trying to marry two very important concepts into one. Okay, we usually think that matter, so people used to think that matter is a different concept from a wave. Okay, those are entirely different concepts, but this time they are now trying to marry the two. So there is now a formulated equation that relates a wave, this is wavelength, and there is matter, the particulate nature of mass. Okay, so Uriel just messaged, but anyway. And then there is also the uncertainty principle. So after relating mass and the wavelength, okay, after developing further the equations, Heisenberg, okay, showed that the more precisely the momentum of a particle is known, because if you have the mass and if you have the velocity, you can actually get the momentum. So he said that the more precisely the momentum of a particle is known, as for this case the electron, the less precisely is its position known. Okay, so what does this mean? We cannot determine both the exact location and the speed or the momentum of an electron simultaneously at the same time. So it's either one or the other. Okay, so that's uncertainty principle. So it gave us it gives us the idea that the location of electrons cannot be pinpointed certainly. Okay, there is no 100% assurance that the electron is there because the electron is moving. Okay, it's both a particle and a wave. So what we have now is the quantum mechanical model, which tells us that electrons are located in specific energy levels, just like in the Bohr planetary model, and it estimates the probability or the likelihood of finding an electron in a certain region of space. Okay, so we'll stop there for now. That is how the quantum mechanical model develops. So there are a series of mathematical proofs, there are a series of experiments that led to the current understanding of the atom and on the behavior of electrons. Okay, we'll stop here and then you may take note down your questions if you have, and then you may proceed to the next video if you have none.